So this is part of a 3-part episode on the origins of life on Earth, from molecules to cells. So we're going to start off by looking at the evidence of life for life on early Earth, and then some of the biological molecules that are necessary for life as we know it, and then we'll move into some hypotheses around how that life and cells formed. So we know and have evidence for life beginning about 4 billion years ago on this Earth. So we're going to look at what evidences we have, as well as what the chemistry of early Earth was like at the time to support that life. So the topics we'll cover include the types of evidence we have, examples of that evidence, the requirements for life in early Earth, and the potential role of plate tectonics in the formation of life in early Earth. So what types of evidence do we have? There's the fossil record, where we have fossils of early microbial mats or stromatolites, which we'll look at a little bit more in a minute. We have microfossils of individual or clusters of microbes showing a cell membrane. And we have chemofossils, which are chemicals that are found within the rock record that are of biogenic origin, something that can only be made from living cells. We also have biogenic isotopic fractionation, which is really the result of the fact that biological processes often favor the light isotopes, and this can be used to corroborate chemofossils and other microbial fossils that are found. So let's look at an example of a fossilized stromatolite, which you can see here as gray and black lines embedded in these rocks. And these are fossils of terrestrial microbial mats in rocks that date back to 3.2 billion years ago. And these are found in the Moody's group in South Africa, representing some of the oldest rocks that have been found on Earth. These rocks were believed to have once been from a shallow marine environment, and isotopic analysis of these structures indicate that they are of biological origin. So what are stromatolites or microbial mats? And actually still many exist in environments today, such as in Shark Bay, Australia. These are a formation of photosynthetic microbes that use sunlight as energy, as well as other microbes and possibly some algae. They form rock-like formations with layers of microbes and sediments stuck together by mucus-like sugars and calcium carbonate that are produced by the microbes. So they form these really lovely rock-like formations that are very stratified or show the layers. And these are some of the earliest microbial formations that have been captured in the rock record. Another example of stromatolites are from the Isla Greenstone Belt in Greenland. And these rocks were formed 3.7 billion years ago. So it's about 500 million years earlier than our previous rock records. And these show internal laminations or layers of the stromatolites as well. And the trace element composition of these stromatolite structures are consistent with other biogenic material. So it's quite convincing evidence that these are in fact of biogenic origin. So let's take a look at some microfossil examples, where we see rocks, again, from the Moody's group in South Africa, 3.2 billion years old, that shows cell membranes here with the dark lines there, as well as complete intact cells, and a longitudinal view of what was believed to be a cell-like structure. Again, these are some of the earliest microfossils we have, other than those found in the Nouveau-Abituk belt in northern Canada. Now, these rocks are believed to have been from ancient hydrothermal vent precipitates that were formed about 3.7 to 4.3 billion years ago. And the dating of these rocks is somewhat controversial. However, there is strong evidence for hematite tubes, which are iron oxide tubes formed from microbial activity. And we can also see filaments here coated with hematite, suggesting some form of filamentous cell-like structure. And these date potential date for early life on Earth back to before 4 billion years ago. So what would life have been like then, or what would the Earth have been like, the environment at that time, and what was really needed for life? There would have been liquid water, which would serve as a solvent and media for molecular interactions. And we need a non-sterilizing environment, or something shielding from UV radiation. The Earth had been bombarded by asteroids, so a large amount of extensive heat and radiation had previously been present, and that would have needed to calm down in order for life to be able to start to take hold and to prevent some of the molecules that were forming from just being broken down again by extreme heat or radiation. But they also would have needed some type of energy source, which was a couple options there. There's light energy or radiation, UV, as well as possible other parts of the visible spectrum, or heat, which was probably abundant at the time, or available redox chemistry. The early Earth environment was anoxic, however, there were lots of other reduction and oxidation reactions likely occurring that were probably a driving force, as well as metal ions for catalysis. So a lot of potential for those metal ions to catalyze organic molecule interactions. So what might have it been like? We know that life probably started after the late Hadean heavy bombardment. So Earth's crust was starting to cool, liquid water was starting to collect, and likely plate tectonics was starting to begin as well. The early Earth atmosphere had no molecular oxygen, probably had hydrogen sulfide, methane, carbon dioxide in concentrations 10 to 200 times more than today's atmosphere, and possible traces of nitrogen or ammonia or cyanide as well. So what was the potential role for plate tectonics in early Earth? Plate tectonics would have made underwater volcanoes and hydrothermal vents. This would serve many purposes: to keep the water warm, provide potential energy by redox gradients, so as intense fluids fluxed out, there would be a gradient of temperature and chemistry and ions, and this would support a diverse array of chemical reactions that would be needed to create the different molecular building blocks that were needed for life. But we're going to hear about it in our next episode here. So in summary, the first evidence of terrestrial life seems to be about 3.2 billion years ago from fossilized stromatolites. The evidence of life in aquatic system can date back to as far as 4.2 billion years ago in the form of microfossils. Life on early Earth would have needed liquid water, protection from being irradiated, and an energy source. Life likely started in the late Hadean, when asteroid bombardment was slowing down and liquid water was beginning to collect. Hydrothermal vents and shallow marine areas were likely places that life would have started.